Okay, our next speaker is Louca Romain. He's talking about sticking properties of dust grains. You good?
Yes.
And I'll give you a 2-minute warning.
Okay. So, hello everyone. I'm Louca Romain, and I'm doing internship with Jean-François Gonzalez at the CRAL in Lyon. And during my internship, I'm studying the influence of the sticking properties of dust grains of different composition on planetary formation models. So I'm studying dust growth in protoplanetary disk, and I'm doing that by launch simulation of a protoplanetary disk with phantom. Now, a brief recap about the context of the planetary formation theory. So planets form from sub-micrometer dust grain size. And as you can see on the left, there is a sketch. This is a sketch of the different steps of the planetary formation. And there's still enough processes to go from centimeter size grain dust to planetesimals. Because in these, there are barriers like the radial drift, which consists of a very fast drift of the centimeter size dust grains toward the star. And again, there is the fragmentation barrier, which is more linked to the physical properties of the dust of the grains. And indeed, an outcome of collision can be sticking or coagulation when the relative speed between the two grains is below the fragmentation velocity, or that can be fragmentation if this relative speed is above the fragmentation velocity. So how the growth and the fragmentation is modeled in Phantom. In Phantom, we use this equation right here. So that depends on the relative speed and on the parameter psi, which define the model that we use. And in Phantom, there are two models. The first one is this one. When psi is equal to 1 is when the relative speed is below the fragmentation velocity. So we have growth. And when psi is equal to -1, the relative speed is higher than fragmentation velocity. So we have fragmentations. The grains are supposed to fragment in this case. The other model is this one. It is more smooth, as you can see here. We have in the blue line is this model, and the red curve is this one. But for my simulation, I use this model. And it's not very physical because it's just +1 or -1. And in reality, we haven't just growth or just fragmentation, but it's simpler than this one. So I use the first model. Now, during my internship, my work was mainly based on the values of the fragmentation velocity. The fragmentation velocity can be expressed like that. So as you can see, that depends on many parameters like surface energy, Young modulus, and so on. So we need to have a good estimation of these parameters in order to have a good estimation on the values of the fragmentation velocity. Because indeed, if we have a bad estimation of one of these parameters, we have a bad estimation of the fragmentation velocity. And now the least well-known parameters is the surface energy. But many studies have been done in order to find the surface energy for different components. And the first one is the silicate. We can see they disagree on the value of the surface energy, but today everyone agree that the fragmentation velocity of the silicate is 1 meter per second. Another component is the dioxide carbon ice. For this one, the fragmentation velocity doesn't extend 1 meter per second. So neither silicate nor dioxide carbon ice are efficient to allow the dust growth in the disk because the relative speed of the grains in the disk reach some velocity of a few tens of meters per second. So the fragmentation velocity of 1 meter per second is very low. But there is the water ice. For this one, again, they disagree of the values of surface energy, but the fragmentation velocity are higher. So that can maybe allow the dust growth in the disk. But again, recent studies have been done and show that the fragmentation velocity of the ice and the water doesn't exceed 1 meter per second. So it's not efficient to allow the dust growth in the disk, and we need other components. So during my work, I find conduit. And for this one, you can see the fragmentation velocity increases as temperature increases. In other words, as we get closer to the star, we have 50 meters per second at 1,400 Kelvin. So very close to the star, as you can see here. And only 1 meter per second around 100 Kelvin, 1000. As you can see, very close again to the star. So the conduit can be efficient to allow the dust growth in a disk, but very close in a disk, very close to the star. Another component is the organic matter. For this one, the surface energy is low, but also is homogeneous. So when I use these parameters in this equation, I found 20 meters per second. And I find in another study that the fragmentation velocity of the organic matter is between 20 meters per second and 50 meters per second. That depends on temperature. So now I found these two components that can maybe be efficient to allow the dust growth in the disk. So I did two simulations, one with conduit and one with organic matter, in order to see if we have accumulation of dust or some grains that can reach a size of few meters or higher. So the first one is the simulation with the conduit. As I said before, I use this very close to the star, and I use the snow line because in Phantom, you can set up a fragmentation velocity that depends on temperature. So the only way to have two different fragmentation velocity in Phantom is to use a snow line. If you don't need to use a snow line, you can just set one fragmentation velocity for all the disks. So that can be interesting in the future to set up in Phantom fragmentation velocity that depends on temperature, because for this study that will be interesting because the fragmentation velocity increases with temperature. And I use 30 meters per second in the inner region and 3 meters per second above the snow line. For this simulation, I extend the disk to this values because that was too long with the values before. So I use this value in order to have the behavior of the simulation. The first result is when you look at the evolution of the gas pressure, you can see there is a pressure maximum like 8 astronomical units. And when you look up at the bottom, that represents the grain size as function of the distance to the star. And the color represents the ratio between the relative speed and the fragmentation velocity. So in red, the relative speed is higher than fragmentation velocity, and the grains are supposed to fragment. And in blue, they are supposed to go. And we see that we have accumulation of dust at the same distance of the pressure maximum. And some grains can reach size of few meters. You can see right here. And we recognize here a self-induced dust trap, an SIDT. So a self-induced dust trap is a dust trap in a disk which don't need a pre-existent structure and creates a maximum pressure and an accumulation of dust at the same distance. And it goes when you consider the feedback of the dust on the gas. Another result is when I plot the theoretical limit size that grains can reach before fragmenting. We can see here when the grains reach this area, their relative speed are higher than fragmentation velocity as expected, so they are supposed to fragment in this area. Now, when I do the simulation for the organic matter with these parameters, again, a disk close to the star, because I found that the snow line of organic matter is at 2.1 astronomical units, but above 3.5 or between 3.5 and 4 astronomical units, we have the water snow line. So that's why we need to do simulation very close to the star. And I did two simulations for this one. Both simulation with a fragmentation velocity of 3 meters per second in the inner region. I consider that grains are silicates. And above the snow line, the grains are silicate recovered by organic mantle. And I did a simulation with 20 meters per second and 40 meters per second. So again, if I extended this because that was too long. And now, when I look again the pressure in the disk, we can see there is a maximum pressure at 25 astronomical units and an accumulation of dust at the same distance. So here again, we recognize nice identity, and we can see that the relative speed of the grains never exceeds the fragmentation velocity, because the fragmentation velocity here is very high, 40 meters per second. Now, when I look at the trajectories of several particles or one particle in the white, I see that the grains drift outward from the star, but it's not physical because, as I said at the beginning, there is the radial drift barrier. The grains are supposed to drift toward the star. So it's the digital artifact caused by the gas relaxation, and that can be solved by launch simulation only with gas for many periods, and after that put the dust in the simulation. Now, when I look the simulation with 20 meters per second, we have the same result. So an accumulation, maximum pressure at the same distance, 25 astronomical units, and an accumulation of dust at the same distance again. So we have again a nice IDT. And for this one, the relative speed exceeds the fragmentation velocity, because indeed the fragmentation velocity is lower than before. So that was expected again. And we have the same problem as before. The grains drift outward from the disk. Now, for the two simulations, when I plot the theoretical limit size that grains can reach before fragmenting, for this one, the grains never reach this area. That's why the relative speed are higher than fragmentation velocity. Let's explain that. And for this one, when the grains reach this area, their relative speed are higher than fragmentation velocity, as expected again, because they reach this area. So to conclude, I did 3 different simulations, 1 with conduit and 2 for organic matter. Both of them give a self-induced dust trap, so allow the dust growth in the disk and formation of bodies of a few meters. And for organic matter, I have a digital artifact that should be corrected by, as I said before, use a launch simulation only with gas and put the dust after. And I want, for the future, I want to do this simulation with it is very close to the star, because that will be more physical. And in this case, if I use the values that I wanted to use at the beginning, so 0.5 and 4 astronomical units, the grains will reach this area. So I will have a different result. And so I think it's interesting to do that. And also it will be interesting to add in phantom fragmentation velocity, which depends as the temperature or the distance to the star, but not just constant fragmentation velocity. And yes, that's it.
Questions for Louca? Sam.
Thanks for the nice talk. I was wondering about the outlet migration thing. You say it's because the gas is not relaxed.
Yes.
Is that something you tried? Like, did you try to relax the gas first? Because I would have thought this is a very fast effect. The gas relaxes very quickly. It looks like in the simulation this can occur longer time. I would have thought it might have to do with the dust not being settled soon, because the dust in the upper layers can actually migrate outwards. That's physical. And so if you don't start with a settled disk, the dust can migrate outwards. Is that something you tried? Like, did you try to relax the gas first? And then,
Yes.
you can have some physical migration. It's not completely numerical. So he tested that it's actually due to the gas relaxation.
Could you please repeat the question, Fizzy?
Yeah, I forgot to warn you. And the microphone won't pick up the audience. So when you're asked the question, could you kindly repeat it to the microphone just there,
Yes.
so that people at home can hear us? Yeah.
That's a long question.
So what's the question?
Have you checked whether it's actually the outward migration was actually due to the gas not being relaxed rather than the dust being unsettled and living in the atmosphere?
I don't really understand your question. What? Okay.
Perhaps I can ask the question another way. So you mentioned that the dust appears to be moving outwards because the disk was not settled first.
Yes.
Possum is suggesting that maybe the dust in the upper layers of the disk far away from the midplane could actually be moving outwards, and that's physical.
Okay.
So is it possible that that's happening, or is it just due to the initial conditions that you have? Is it possible that the dust of the upper layers is moving outwards, and that's what you're picking up?
I don't think, because when the grains go to the middle plane, and they go very fast to the middle plane, so there are the most proportion of the dust is in the middle plane, and here, yes, we see that a lot of grains just outward from the star. But I can look the initial altitude of these grains, and I will see if these grains are grains which are in the upper layer, or if they are in the middle plane. But I think it's just a digital artifact, and it's just a question.
Thank you. Francois, a quick question, please.
Yeah, so just regarding your setups, the simulation with chondrites. Like,
yes.
Your disk is full of chondrites, or like what's the fraction of them in the disk? And same question for the other with the organic matter. It's you put organic matter as a mantle around silicate cores, or like.
With chondrite, it's full of chondrite, and with organic matter in Phantom, you can just set the density of the grain. So you can just set one density for all the disk, not for two different regions or other. So the way to just the difference here is just the fragmentation velocity, but it's the same grains because it's the same density, and that's it.
Just to clarify, maybe Jeff can comment. We do set a density per part. We do store a density per dust particle. Is that correct?
We don't use that for the moment.
Well, we could.
You could.
Yeah.
It was a very preliminary.
Yeah. It's not technically impossible.
No.
All right, well, thank Louca again.
Okay.